My topic is the RF exposure evaluation that we were surprised with a few months ago. And a lot of folks got kind of concerned about it, so I've named this Demystifying It. Some of you may know as much and more than I do, but I'm going to try to make it simple. I'm going to move fairly fast. If you have questions, preferably save them toward the end, because if we get too many questions in here, it may make this last a little bit too long. Back in April, we had this announcement on the ARRL website and in the ARRL letter and QRZ and a bunch of other places announcing that in 3 weeks' time, the new RF exposure rules became effective. And hams were going, why now? And why such short notice? And there were people on 80 meters accusing the FCC and the government for just wanting to get our frequencies. But is this RF exposure stuff something new? Well, it kind of goes back to the 1890s. A fellow by the name of D'Arsonval and Tesla were doing some work on electric shock therapy, and they were using alternating current so that the muscles of the body weren't so badly disturbed. And they found that if you got up above 10 kilohertz, it was easier to handle. But they also noticed that the cells inside the body kind of got warm at times. And so D'Arsonval speculated that this might be useful in medicine, and it later became known as diathermy. This is still around nowadays. Shortwave RF is used as well as microwave. Over the years, as long as we've had radio, people who've been involved in radio have commented in their logbooks and in their notebooks of feeling the effect of RF. There's been a lot of scientific papers, well, a lot of unscientific articles in newspapers too, talking about the effect of RF. The general public, people who lived out in the hinterland, who suddenly had the 60 hertz transmission lines built on top of their houses, were noting the effect of 60 hertz. And along came World War II. We had a lot of development of high technology. Following that, personal radio blossomed. A lot of handheld radio telephone systems were starting to occur back in the 1960s. And so in 1969, the federal government kind of consolidated all of the concerns about the environment. And one of those had to do with the effect of RF on humans. So this act in 1969 directed the FCC to evaluate the effect of RF on humans. This helped out some non-government organizations, ANSI, the IEEE, and the National Council on Radiation Protection and Measurement, to get a bunch of government grants to do some studies, but also to collect all the different papers that have been presented over the years and see what they could make out of them. After this act was formulated, it took about 13 years for the IEEE and ANSI to really get together and develop some recommendations. The FCC picked up on those, and the IEEE kept on working on the information that they gathered. And 10 years later, the FCC finally came up with a notice of proposed rulemaking and with the standards that had been developed, and they came up with a report and order. But then there was 4 more years that went by and 2 more years. You know how the government is. And finally, in 1998, there were the rules for radio amateurs involving radio frequency evaluation. Now, a lot of folks say, I've never heard of this, but since 1998, beginning with Form 610, which was the old amateur radio application form, and later became Form 605 and the NCVEC 605, the statement is included. I've circled it in red. Chances are you never read it. All you did was sign this document under penalty of perjury. I have read and will comply with Section 97.13C of the Commission's rules regarding radio frequency radiation safety and the amateur service section of OST OET Bulletin number 65. Well, here's what 97.13C says. before causing or allowing an amateur station to transmit from any place where the operation of the station could cause human exposure to RF electromagnetic field levels in excess of those allowed under Section 1.1310 of this chapter, the licensee is required to take certain actions. The first one was, it now reads, ensure compliance. It used to also have additional wording that allowed certain exemptions. Section 2 then, take corrective action if not compliant. Well, even though this was initiated in 1998, there were a bunch of exemptions allowed to all kind of FCC licensees. 2 years later, the FCC finally came along and said, everybody's got to comply with it, with exceptions. Well, 19 years later, a report and order came out, and it took them 2 years before this May 3rd date showed up. And it said basically that the RF exposure standards finally go into effect. Amateur stations could no longer categorically be excluded from certain aspects of the rules. New stations or existing station modifications would require evaluation. And it turned out if you fit under that old categorical exclusion, which you were adopting that, then you had 2 more years before you actually had to do the evaluation. This does sound like the government, doesn't it? Anyway, what was that categorical exclusion? Well, it was a table that looked like this. It said basically, if you had a station in which your transmitter power didn't exceed 500 watts on the 160 meter through the 40 meter bands, you didn't have to do anything. All you have to do is to say, I'm accepting this exclusion. Then you notice as the frequencies go up or the meters go down, the amount of power that you could have went down, so that if you had a typical 100-watt station, you could go up to 15 meters with no issues. And if you said, well, I don't really operate on 12 meters, so don't worry about that. And on 10 meters, there's not much activity, or if I do get on, I'll limit it to 50 watts. Then you could use this categorical exclusion and get by without doing anything. Well, now we have to do something. So where do you find out more information? On the ARRL website, there is a page, RF-exposure. And by the way, at the end of the presentation, I'll have a list of all the URLs that I'm going to mention in here. If you want to take a screenshot at the end or use your smartphone to take a picture of the screen, or if you'd like for me to mail a copy to the secretary or somebody who will distribute it, I'll be happy to do that too. But on the ARRL RF exposure page, there's a fair amount of information along with news and a bunch of articles. Now, I'm not going to go over all these other than to point out this is a list of all the different articles that are available to read. It'll keep you busy, especially, well, I can't say on those rainy nights anymore because I think it's going to be dry for a while. The 2 documents that probably make the most sense for you to download and save and use for reference is this OET Bulletin 65 Supplement B. OET is the Office of Engineering and Technology. They came up with this document, and it's gotten revised a couple of times. The ARRL produced a book that they used to charge for because it was a hard copy, actually soft copy. It was printed. RF Exposure in You, written by Ed Hare, W1RFI. It's a very good book. It includes the portions of OET Bulletin 65 and OET Bulletin 65 Supplement B that's really critical. So one thing makes it easy to read everything. This is now available free of charge as a PDF to download. It's very accurate. There's nothing wrong with it. The only problems you have with it is the URLs that are mentioned in RF Exposure in You, and the same thing in OET Bulletin 65 Supplement B. Many of those URLs or web addresses are no longer alive. So you go to them and you're told that they don't exist anymore. But this book, RF Exposure in You, is a very valuable book. But I tell you, if you start reading those two documents, it can make your brain explode. There's all kinds of equations that jump out at you. There's graphs, there's charts, there's all sorts of stuff, and it can make your head spin. So there must be an easier way. I call it the KISS method, the keep it simple method. And we're going to use this in terms of evaluating RF exposure. In both of those documents, there's 6 different methods that are recommended for amateurs to use for RF exposure evaluation. Of those 6, I've checked 3 of them that make the most sense. The first 2 up here is using the tables that are in those documents that are developed from field strength equations or derived from antenna modeling. And those are very useful. The other one that's very good is using software developed from field strength equations. Now, when you start looking at this list, and it's very inviting, you see this last one down here, using calibrated field strength measurements. Well, that sounds like something that would be nice. I just walk out there, hold this meter up, and it tells me if I'm okay or not. The trouble is that the kind of device that you would use is in the price range of $3,000 to $6,000. Plus, these things have to be calibrated at least once a year at a cost of $300. The manufacturers of this equipment tells you that a skilled user can generate measurements that are plus or minus 2 dB accurate. Now, the 2 dB doesn't necessarily apply to 2 dBm or any kind of a specific measurement, but it can simply give you variations that will not give you the accuracy that you'd like to have. If you want greater accuracy, you can get involved in a lot of training, which is not free, not like ham radio classes, or you can spend a lot more money for equipment that is uses fiber optics to interface to it, so you don't have to be close to the equipment. You can operate it remotely, and you're talking $20,000 to $30,000. This handheld equipment in the hands of an unskilled user is probably plus or minus 10 dB. That's probably like a typical ham who picks up something, equipment like this, and doesn't read the manual first. So I tell you, using prediction calculation tables that are free is a lot more inviting to most ham radio operators. When we get involved in RF evaluation, there's 2 environments that we have to consider. You may have already read about these somewhere. One's a controlled environment, the other is an uncontrolled environment. The controlled environment, also known as an occupational environment, well, because this RF exposure is not just for hams, it's also for the commercial industry, for radio and television and everything else. But the controlled environment is the ham operator and his or her immediate family. Something about it is the controlled environment is evaluated over a 6-minute period. It's got a different time frame than the uncontrolled environment, which is for the general public. Uncontrolled is your neighbors and any public areas around your home. This exposure is evaluated over a 30-minute period, so it's a 5 times more severe type measurement. You might look at it this way: your home and your property that you live on, especially the property that is fenced in some way or that you have control over, is known as the controlled area. This is something where you can say, I know who's on my property. I know whether if I'm transmitting, those people are going to be affected. The uncontrolled are the people outside your property, someone on your sidewalk, your neighbor's property, and that sort of thing. It's interesting to note that the FCC in their documentation says that the thoroughways, streets by your home are not necessarily considered to be part of the uncontrolled environment. We don't worry about those people. The distances we will be talking about are these direct point distances. So if the end of the antenna is here, the distance we are talking about to the point of interest, which is like the person, is the straight line distance as the crow flies, if you will, or into the house like this. We're not talking about the height of the antenna from the ground or the horizontal distance of the antenna to the person or point of interest. It's the straight line from the antenna to the person or the point of interest. There's one more terminology I'll mention. If you're looking in the documentation, they'll reference it a number of times. It's called ground reflection. From any point on the antenna, there's going to be a direct correlation of radiation to the point of interest. There is also radiation that goes to the ground and reflects and goes back to the point of interest. So you have to sum those additional points of energy. The same thing, each of the different elements on the antenna has a direct effect on the point of interest and also has a ground reflection to the point of interest. The good news is we're not going to worry about this other than my pointing it out to you. That's what ground reflection is. We're going to use the KISS method. It's the worst case method. And this is the one where we're going to assume a bunch of things. First, whatever your maximum transmitter power is that you're going to be using is what we're going to use in our calculations. We're also going to say that our transmitter is keyed down continuously. We're also going to allow for ground reflection, and this is taken into account automatically in the equations. Also, we're going to use the closest part of any antenna to the people or points of interest. We're not going to say it's the center of the antenna or it's an average part of the antenna. It's the closest point, and that's where we measure the distance from. Also, the assumption is that any part of an antenna can radiate maximum energy. When we're talking about the gain of an antenna, we're going to be looking in various places. Antenna books like the ARRL Antenna Handbook, manufacturer specifications, that's a very good source, or models. And whatever one of those we look at, we're going to pick the maximum number that comes from any of those. This is the KISS method, the worst case method. Antenna gain is typically measured in dBi. So here's a good test for you. What's the I stand for?
Isotropic, I think.
You got it. Isotropic source or isotropic. It's a pinpoint. It's just simply like a little dot. And whether it's 1 watt, 10 watts, 1,000 watts, 10,000 watts, 1,000,000 watts, is simply a pinpoint source. It radiates equally in all directions. Now, think about a dipole. A dipole is represented by this blue line right here. So the radiation off that blue line off a dipole is off to the sides. And there's very little that goes off the end, if any. And so it's kind of like taking this isotropic source, considering it a beach ball, and squashing it down. So we form this donut shape. When we do that, the energy that could have been going in an upward direction is pushed out to the sides. Imagine that. And so the red and the green that we have off here shows that this is where the highest amount of energy is going to be going off that antenna. For a dipole, then, we say the gain is 2.2 dBi. That's to keep it simple. In actual calculations in free space, it's 2.15. But what's 0.05 among friends? So that's the number we're going to use. When you go to HRO and you're looking at antennas, especially mobile antennas, you're going to see that some of them are specified in dBd. The second D refers to decibels referenced to the gain of a dipole. So 1 dBd is equal to 2.2 dBi. Because that's the gain of a dipole. That's what that stands for. So if you're looking at gains in dBd, you simply add 2.2 to get the value in dBi. So if you looked at one of these mobile antennas and it said it's rated as 4.6 dBd, you take 4.6 and add to it 2.2, that gives you 6.8. I mention this because frequently I've overheard hands at HRO looking at antennas, and they see one that says 4.6 dBd, another one says 5.4 dBi. Well, I'm going to buy this 5.4 because it's got a bigger number. But that isn't the case. They forgot that the DBD has to have 2.2 added to it for the proper comparison. So everything we're going to use is measured in dBi. Again, those distances are measured by the closest point of the antenna. In the case of a beam, it's wherever the points of interest are located, and that's the outermost part of the antenna measured to the points of interest. In the case of a dipole, we've got wires off to the side like this, and we have feed line going to it. And so any point along here that's closest to you is where we measure from. But now if this is a shortened dipole, if it's a non-resonant, or if it's something like a G5RV, an off-center fed dipole, a Wyndham, this twin lead, or in the case of a Carolina Wyndham, this could be coax, is more than just a transformer. It's also part of the radiation system. It's a radiating element. So we have to consider radiation off that feed point, that feed line. It looks like a feed line, but it's also part of the radiation system of the antenna. Here's the vertical. The typical vertical, power goes off both ends of this, and we think, okay, that's where we measure from. Not quite. If you've got these things down here called radials, you have to take, the radials are part of the radiating system. They normally are laid on the ground. They're the counterpoise. They are part of the radiating system of the antenna. Some people bury their radials a little bit too deep. They go down there and they take a trencher or something, and they go down a foot before they put the radials. You go down below like 1.5 inches, it's no longer a radial, it's just a ground rod. You might as well just have put a single ground rod and forgot about it. But if you have true radials down here, whatever these points are that are closest to you, that's where you measure from in the KISS method, in the worst case method. In the ARL book, RF Exposure in You, on page 514, I'm not asking you to memorize this, there's a table 5.5. It's a worst case method chart, and it tells you this. This thing assumes continuous key down and ground reflection. And I'm going to zoom in on this so it's easier to read. Take a part of this. This table is organized according to transmitter power, or our power at the antenna, however you want to use it. It's 100 watts, 500 watts, 1,000 watts, and 1,500 watts. If you have power that's in between those, you can use a little bit of arithmetic and do interpolation, but it's a pain in the rear, so we'll come up with an easier way to do that. There's also the different frequency bands that are shown as a nominal frequency. Here's 160, 80 meters, 40 meters, and like that. You don't see 60 meters in here because 60 meters, when this chart was created in 1998 and later in 2001 when it was updated, we didn't have privileges there yet, so it's not in this chart. The gains that are shown are typical kinds of gains for the kind of frequencies you're dealing with. Chances are you're not going to have a beam for 160 meters, same thing for 80 meters. There are a few folks around that have something like that, but it's not till you get to 40 meters that it's practical to start achieving some gain. And up here on 20 meters, for example, you can see a Yagi, even a very good vertical, having some additional gain. So these are in 3 dB steps. If you wanted to go in between, then you can do some interpolation of these numbers. But again, that's a pain in the butt. The easiest thing to do is if you're talking about a dipole, take, for example, the 80 meter band. If you had a dipole, it's 2.2 dBi. So that's between 0 and 3. Well, that's closer to 3. Just use the 3. So here, take a look at this. On this chart, this is assuming continuous key down. It's the worst case. If you have a 100-watt radio, your control distance needs to be about 1 foot away. Not bad. Your uncontrolled has got to be about 2 feet away. Well, look, if you have an amplifier and you're operating 500 watts, you only, as the control operator, have to be about 2 feet away from that dipole, and your neighbor only has to be about 4 feet away in order to be safe. As we go up in frequency here on 20 meters, Here we have, let's use that 3 dB point and go over here to that 500 watt thing where we were just a few feet back on the 80 meter band. Now we have to be 7 feet away at 500 watts for the controlled operator and about 16 feet away for the neighbor. So if the antenna is up at a reasonable height, you shouldn't have any issues with this. As we go up in frequency and as we go up in power, you start noticing that those distances are increasing. And this is true on the high frequency band down here at 160 meters. This is your safest frequency. Look up here at 1500 watts with a dipole. You only have to be 3 feet away in order to be for the control operator and 4 feet away from your neighbor. Wow. But now you get over here for the 20 meter band and on 1500 watts, you've got to be 12 feet away. Your neighbor's got to be about 27 feet away. Still not too bad, but if this antenna is mounted right up against your fence in the backyard, you're encroaching on your neighbor. We want to keep you and your neighbors safe. The thing we have to consider, some hams have said, I'm just going to put my antenna up high enough so I'll be safe. Well, what if your neighbor's house is relatively high also? You see, this is something we have to consider. Not only is it your height above you for your own property, but your neighbor may be close to your property and may be high, may have a 2-story or a 3-story house. And so now your energy may be breathing right down your neighbor's back. Also, we have to consider some of the radiation patterns of antennas. Yagis don't necessarily, even though we think about it as having energy right off the end, you're going to find that with a Yagi antenna that the radiation, the most intense part is going to be at a slight vertical angle and a slight downward angle. So those things have to be considered. But for our worst case right now, what we're looking at is the distance from the antenna to our point of interest, which is the person, whether it's you and your property or your neighbor. Now, remember I told you that the lower the frequency, the safer it was, the higher the frequency, the worse it was. So here's 10 meters. If you're looking at perhaps a multi-band wire antenna like an alpha delta, and it's got various bands on it. If we're here at 10 meters, and we'll use this 3 dB point for a dipole, and we're dealing with 100 watts, then for our worst case, our antenna's got to be roughly 7 feet away from us. And more than likely, if you're going to have this antenna up outside your house on some poles or up with a center pole, you're not going to have any problem achieving that 7 feet. You've got to make sure that for the uncontrolled area, your neighbor, public areas, that any part of your antenna is at least 15 feet away. If you're going to operate with a lot of power, then you have increased distances with that. And we'll talk about how in the world would you mitigate that. But right now we're looking at this continuous key down and ground reflection as being the easiest way to evaluate what kind of distances we need to achieve. Table 5.6 is on the next page, and it covers the VHF UHF bands. It's very similar to the other one. It has 50 watts on up to 1,000 watts. You'll notice that the 6 meter, 2 meter, and the 220 bands are all lumped together. They have the same absorption rate in the human body. And there's a lot of different gains that are shown here because it's easier to put Yagis together at these different frequencies. And some people are building some pretty good size antennas for things like moon bounce, or if they're serious about working VHF, UHF. Now, if you had a vertical on the roof and you're on the 2 meter band, for example, that vertical is going to have a gain probably around 6 dB. So you've got to make sure that any part of that vertical is at least, we'll say, 7 feet away from your operating position or your family. And it needs to be roughly 15 feet away from your neighbor. And a lot of the kind of verticals that we put up on our houses are on the center part of our house, on the chimney, somewhere like that. So this tends to be okay. That's going to be an okay distance from your neighbor. 50 watts, very popular because that's what the power rating of mobile radios is that we tend to use for base stations also. On the 70 centimeter band, things actually get a little bit better. Here, if we have a 6 dB gain, we only have to have 5.6 feet compared to 6.6 feet. And from our neighbor, 12.5 feet compared to 14.8. So that's just kind of gives you an idea how you can use these charts. We'll be using the charts, and we'll also be using the online calculators. Just remember, all distances are measured from any radiating parts of an antenna. You measure from the closest part of the antenna to the point of interest. And the thing we are dealing with in terms of radiation is any part of the antenna, any radiating matching stubs, or any radials that are involved in the antenna. There's a calculator that's available to you, and the ARRL has now taken the calculator that was on the Lake Washington Ham Club's website and revamped it. Actually, just took the code, changed a little bit of the cosmetics, and put it on their website. This is good. The Lake Washington Ham Club was being sponsored by a number of radio companies to help make sure that the website stayed there. Over the years, there were a number of very good calculators. There was one at the University of Texas at Austin. I don't brag about it because I graduated from there, but it was the best around. And probably because the professor or whoever was sponsoring it got promoted, got fired, or who knows what, but the thing disappeared. And so now these guys came up with a very good calculator. Be cautious about some of the calculators you may run into in foreign countries like South Africa, Great Britain, especially in Russia. They use some different standards, and so you may be fooling yourself when you use their calculators. But the one that's on the ARRL website is very good, and there is another one I'll tell you about. This VP9KF, Paul Evans has created one. It's a little bit different, but what I like about it is it allows you to see the actual power density at a specific distance, whereas the other one gives you the maximum distance that you need to be in order to be in compliance. This is going to be useful if you're dealing with multiple transmitter locations, like at field day, or if you have multiple things going on at your house at the same time, or even for evaluating repeaters. So the one at the ARRL looks similar to this. At the antenna, you put the power in here. Now, for what we're going to do for the worst case is we're going to use the maximum power out of your transmitter. And the reason we do this is to keep it simple. If you want to, and if you're having to mitigate things, you found that you have a little bit of a problem, you may consider the amount of power that you lose in your coax if you're having to go over 100 feet, for example, the losses in connectors, the losses in balance, switches, any other things that you have on the way to the antenna. And so that could reduce your power somewhat. The next thing is the mode duty cycle. Depending which kind of a mode you're using, it will have an impact on what is known as the mode duty cycle. So this has a drop-down menu. Let's take a look at that. If you're dealing with conversational single sideband and no speech processing, the duty cycle is 20%. If you're using a lot of speech processing, it's 50%. CW, conversational CW, is 40%, and everything else is 100%. FM, even though you say, well, that's sort of conversational, the trouble is the FM signal is there all the time. It's kind of like the AM carrier. With RIDI, you've got a RIDI signal present all the time. AFSK, a la FT8, it's there all the time. There's also one called Carrier Always On, like for tuning. And if you don't know what it is, you click on this bottom one and you're penalized with the duty cycle of 100%. So let's see. Transmit duty cycle is the next one. Remember, for your control, you're dealing with a 6-minute time frame, And for the uncontrolled, you're dealing with a 30-minute time frame. So these things become important. Now, I point out this calculator that's on the ARRL website will take that into account automatically as two different calculations. The one that's on that fellow from the Bahamas, you will have to do your own calculations of all these duty cycles and take them into account. You have to do two different calculations in order to get your controlled and your uncontrolled. You see, if you're transmitting for 5 minutes, for example, and then receiving for 10 minutes in this example, for the control aspect, this is 5 minutes out of 6, which represents an 83% duty cycle. For the uncontrolled, you're transmitting for 5 minutes, listening for 10 minutes, transmitting again for 5, listening for 10. That means 10 minutes out of that 30-minute time frame, which is 33%, a little bit different. Well, now we know we have two different duty cycles. The antenna gain in dBi, this is the one that is associated with your antenna. And on the ARRL website, they've got a table here that can help you out if you don't want to go looking anywhere else. They have the Radio Society of Great Britain's field exposure tables that have been copied over. These are handy, and you can just simply use these. If you're dealing with a dipole, you can use 2.15 or 2.2. For a different kind of Yagis and for the number of elements, this is fairly close to the correct amounts here. Interestingly, on the G5RV, they say 1 dBi, and there's a lot of arguments about this. This is probably at the fundamental frequency of the G5RV, because at the harmonic relationships of the G5RV, it's going to be different gains. And this is not taken into account, but I'll show you something in a moment. The Wyndham, they say, is 2 dBi, and this may be a little bit low. You may have to consider something a little bit higher. But these are still okay to use. It's enough to get you going. Now, I mention this because here's something about modeling. A friend of mine, KK4OBI, created these models for a full-size end-fed half-wave 80 through 10. It's 130 feet long. So you see here at 80 meters, it's 1 dBi. That's the fundamental, and that's kind of like that G5RV fundamental. At 40 meters, it behaves more like a dipole, 2.1. So you get over here to 30 meters, it's around 3 dBi. Then 20 meters, it's almost 4 dBi, 15 meters, 5.5, and 10 meters, 4.6. At different elevations or different heights, this number could have been a little bit higher for this model. But as you're going up in the harmonics, you start getting these weird patterns. The red is the horizontal propagation, and the blue represents the vertical propagation in terms of the gain. But for any one of these, we'll be using whichever band we're going to be using. We pick the highest rating for us to see what that's going to be at a particular frequency. All these kind of models, by the way, are on the Bent Dipoles website. This is a very useful website because for those of you that have limited space and you're thinking, how do I put this dipole up? You'll discover that you can bend the living daylights out of dipoles and not even affect their performance that much. So let's go back over here to our chart again. The worst case charts, continuous key down and the ground reflection. This one, you remember, has 100 watts, 500 watts, and so and so and so. So how in the world, if you had a 200 watt radio, would you figure out what that is? Remember, I said you could interpolate. So a 200 watts in whatever we would use in here. Let's just pick one, for example. If it was on the 40 meter band and we had a dipole and we wanted to look at the control, it would be between 1.6 and 3.6. And I'm trying to figure out where to put that 200 watt marker in here. What would that distance be? Well, that involves some mathematics, and we don't want to do that. So we're going to use the calculator to help us out. So here's going to be the worst case analysis for a 200-watt rig on 40 meters. 200-watt rigs, we're going to assume worst case 100%. We're going to key down 30 minutes, receiving for 0, antenna gain of 2.2, the operating frequency of 7.2, and include the ground effects and calculate. And what we find out is our minimum safe distance is right at 2 feet. And for our neighbor, the minimum safe distance is around 4.5 feet. And for 40 meters, 200 watts should be pretty easy to achieve. The other thing is if you have a multi-band antenna, like maybe an alpha delta multi-wire multi-band, and let's see what this is going to be on the 10-meter band, which is going to be your worst case condition. So how high and where do we have to put this antenna? 200 watts, 100%, everything else stays the same, except this frequency, 28.5. Let's calculate. Now it says our ham needs to be 8 feet away, and our neighbor needs to be at least 18 feet away. And so if the antenna is up in the air, we'll just say a reasonable amount, 20 feet up in the air, then as far as our controlled area in the backyard, this is something we have to consider. Someone in your family walking around in the backyard, you have this 8-foot distance, and the average height for a human being is 6 feet. So that's 14 feet. So if the antenna is up at 20 feet, then you shouldn't have any issue with that. But your minimum safe distance now for your neighbor, suddenly, if this antenna may need to be kept away from the back fence a little bit, so that if you consider your neighbor standing right by the back fence, you have the height of that neighbor measured over to where the antenna is located in order to make sure that you've taken care of that 18 feet distance. Now, what happens if you can't achieve success when you do this worst case? You can relocate your transmitting antenna. That's an easy way. You can choose a different antenna. For example, you can have a vertical antenna closer to your house that gets it away from your neighbor. Might make it in some reasonable distance from your house, from your operating location. You can also control the pointing of a beam. But you know what Murphy's Law says? The direction that you've got to be pointing your beam is the direction of your house in order to work that rear DX. You can reduce the transmitter power. That's the easiest one of all. Use a different mode, and I'll show you an example of this in a little bit. You could also reduce the amount of time. Yesterday, I was listening to some guys talking on 20 meters, and I swear each guy, I didn't time them, and they did ID at least. Each guy spent about 40 minutes each talking the entire time. Change the operating frequency. If you go to lower frequencies, then the maximum permissible exposure limit is higher, the lower you go in frequency. The FCC says, in addition to fencing in your backyard or fencing in the areas where you have antennas, you can also put up signage. They say that that's acceptable, something that says that there's RF energy or no trespassing, or it can be a mixture of these different things. So in our worst case chart for 10 meters, if we had a beam antenna and we just have to use 1500 watts because life's too short for QRP, we've got to make sure that our control distance is 50 feet away. And if you have a typical city ordinance and a typical size yard, your tower is possibly not going to be high enough to achieve this 50-foot marker right here. And with the kind of sizes of properties we have, you may not be able to achieve a distance of 113 feet from your neighbor's backyard. So what can you do? Let's use the calculator now. 1500 watts, change this to conversational single sideband with no speech processing just to see what's going to happen. We're going to transmit for 2 minutes, receive for 2 minutes. So that's a 50% duty cycle. It's a reasonable amount. And the antenna gain 9 dB. This is very typical for a Yagi on a 28.5 and include ground effects. Now we see that our minimum safe distance for our ham shack for the operator and his family is roughly 18 feet. That's a little bit more reasonable. And if we're sitting up at around 30 feet, well, actually, if we have a 30-foot tower, maybe a mast that gets us up an additional 5 feet or so, we are high enough that from a height standpoint, we now have this 35 feet. And if it's not right up against the neighbor's fence, we shouldn't have any issue with our neighbor. So we were able to simply mitigate this by saying we're operating single sideband. We couldn't use the worst case. It said to us, you're using too much power, but by changing the modes, we're able to see that we can get by with using single sideband, no compression, or even light compression, and we shouldn't have any issues. The distances we're talking about, it is the closest point of the antenna measured to the point of interest. And so it's the antenna, not the center of the beam, but the end of the edge of the beam measured over toward your neighbor, whether your neighbor is standing in the backyard or whether it's your neighbor's house. So those are the distances that you talk about, those as the crow flies, the straight line distances. Look at the comparison. So 17 or 18 feet versus 50 feet, and the uncontrolled now 36 feet versus 113 feet. And we were able to do that by just using the calculator to change the operating mode. Now, in the OET 65, there was a supplement C in the old days. It's been replaced with some new documents. C has gone to the wayside. It's interesting. You'll see on the ARRL website that they still reference C. You can find it in some places. The FCC doesn't make it available anymore. They have different documents that replace it. But in the old C, it said for the UHF, VHF bands, handheld radios, radios with 8 watts or less were no problem. Well, that's been changed. Let's take a look at what we have to do now. 5-watt radio. We're going to use this on the 2-meter band. FM duty cycles 100%. Let's use the typical conversation, 2 minutes on, 2 minutes off. If you're at a public service event, there's a very good chance that you may be transmitting for 1 minute and receiving for 15 minutes or 30 minutes, who knows what. So that could change. But right now, let's just say we have a conversation, a back and forth. Let's use an antenna gain of 0.5. You'll see online that a lot of people use a 0 because a rubber ducky is kind of like a wet noodle. It's actually a negative number, but 0 would be better. But let's just say we have a nice diamond antenna and it's a 0.5 and see what that does for us. It says that your antenna needs to be roughly 1 foot away from a point of interest or a human, which is your head. Well, if you're holding it right by your head, the way we typically do, you're not able to achieve that. For the people who are around you, the unsuspecting masses, they've got to be at least 2 feet away. So the thing we have to do is to move that away from us. Use a headset, use a speaker mic, hold the radio away from you a little bit. There's a few things that are mentioned in the RF exposure in U that I'll mention here. With the handy talkies, you want to keep the antenna away from your head. Use the lowest possible power. Hold the rig as far away as possible with a speaker mic or a headset. A lot of folks have been coming up with some sort of a little contraption that they mount on a tripod to mount the radio and their speaker mic on it, so that when they can hear it, and then they can grab the speaker mic and they're able to move away from it. A few other people have mounted an antenna on the top of a pole and got it away from a little bit, even mounted it on a backpack so it's several feet above their head. So that's another possibility. Lido mounts makes these things that are shown here. There's a beverage holder mount that you can modify to go in a tripod. This is a bicycle mount. So those are commercial ways of doing it. You want to keep the RF radiation confined to the antenna. This is important. You need a good station ground. And the word single is very important here. Now, I know you're going to have multiple grounds, but if you have multiple grounds, you've got to run a very heavy wire between every ground that you have so that there is a single station ground. And that includes your 60 hertz incoming power to your house, as well as any telephone grounds that you have. You want to eliminate radiation off the transmission lines. If you key down your mic and your mic stings you a little bit, or you touch your cabinet on your radio and it gives you a sting, you've got RF coming back. You also want to bring coax into your ham shack. This is not 1920 anymore. Don't bring an end-fed wire in or even open wire lines. As soon as you can, when they get up to the edge of your shack, convert them into coax. You don't want to operate high power amps with the covers removed. The covers are there not only to make it look pretty and to keep you from touching something, but to keep the RF confined. Never look into the end of waveguide or a microwave feed horn. Not a good idea. And at UHF all the way into microwave, don't point antennas toward anyone when they're active. And if you don't know if they're active, you assume that they're active. Never work on antennas if the power is applied, if RF power is applied. I will tell you this, the worst burn you can have is an RF burn. It burns from the inside out. It can take months to heal, and it can even take years before the muscle tissue regrows, if it ever does. Also be concerned about 60 hertz magnetic fields from high power transformers, big electrical fans, and other sources that use 60 hertz. It's recommended to stay at least 2 feet away from those kinds of devices. So let's summarize what we've talked about so far. If your station was exempted prior to May 3rd, you have until May 3rd, 2023 to perform an actual evaluation. Now, what was that exemption? That exemption was if you can say, I've got something like a 100-watt station, and so on 12 meters and 10 meters, I either didn't operate on them, or I can, I won't go above 50 watts, at least for a while. You've got 2 more years before you have to do anything if you're willing to confine yourself to that. That was the exemption that we had. If you had more power than that, then you couldn't be exempted. And but I will tell you, if you performed an evaluation before May 3rd of this year, that's all you have to do. You've already done the evaluation. Now, whether you did that evaluation in writing, or you did that evaluation, you scribbled it on the back of a napkin, or you did it mentally, that's all you have to do. Now, if your station wouldn't qualify for the earlier exemption, or you modify your station, you change your antennas, you increase your power, you've got to do an evaluation. I recommend using the worst case KISS method first. Written records aren't required, but they're a good idea. With our memories nowadays, how do you remember if you did it, and what were the details of why you did it and how you did it? You see, safety for you as the ham and safety for your family are important. This is serious. And you also want to take care of your neighbors, because if there's some reason that you're affecting your neighbors, you want to know that. You want to try to avoid this. It's a good way to document your station configuration is by coming up with some written records. Here's a few simple ways of doing this. If you've bought your house in the last 20 years or so, if you refinanced, chances are you've got a record of your property, and it shows where your house is and all the different things on your property. As a minimum, you can go to the appraisal district website. You'll get an outline of your property from them. May have to blow it up a little bit, and chances are They even have an outline of your house on your property. So what I did was I took this outline of my property and I plotted where I have a couple of antennas. I have an end-fed half wave here in the back and a vertical here behind in the back part of the lot. Also for the end-fed, this drew a little vertical sketch. It starts out over here behind my house and runs across the property to the top of a tree. And I estimated what the distance was over here to the fence. This is where the sidewalk is located right over here. That's 25 feet. I took that worst case chart. I like to do things simple. And I said, okay, for the end-fed half wave, based on those estimates that my friend had done the modeling on, I have discovered I can operate on 160 meters with it. I figured the gain was zero. 0 on 80 meters, 3 dB on various bands until I get up here to 15 meters. I figured it was around 6 dB, 3 dB back here on 12, and then 6 dB on the 10 meter band. And the worst one for this then was going to be on the 10 meters, which meant I had to be 10 feet away. And when I look at my control distance, this distance over here to where my ham shack is located, my ham shack is on the second floor and it's sitting right over here. So that distance is close to 35 feet actually. I've only got to be 10 feet away, so I'm safe. This is also the garage, and so I know that there's not going to be anybody around here. This is the patio area, and there's cameras that watch that. If anybody walks outside on the cameras, I get an alert on my phone as well as on some other devices here in the ham shacks. So I'm alerted to somebody walking out there. So I feel like I'm safe. 21 feet is how far I've got to be away. And this chart right here shows that my straight line distance is 25 feet to the top of this fence. The fence is right at 7.5 feet tall. So I shouldn't have any issue with a 6-foot person here. So I meet all the requirements. So that was my easy way of documenting stuff. Well, I'm going to close it out with how do you handle a multi-transmitter site? The way you handle a multi-transmitter site is a little bit different. You've got to determine the percent maximum permissible exposure from each of the transmitter antenna combinations for the worst case frequency band for that combination. So you figure out for whatever that is, because mainly we're looking at distances here, powers and the types of antennas, we're going to come up with this percent. You do a simple summary of percentages. That's easy enough to do, not a whole lot of math here. If you add it all up and it's less than 100, you're okay. If it's greater than 100, you got to follow some mitigation methods. Instead of using the worst case, then you may have to go and reevaluate it based on the types of modes that you're using or different times. I mention this because in the chart about power density, you'll notice here in the high frequency band, it's related to frequency. On certain bands, it's just a whole number. But on certain other bands, like on the UHF and microwaves, the frequency gets involved also. The same thing is true for the uncontrolled. For my example, I'm going to use here quickly, the Collins Amateur Radio Club for many years has been operating as 3 Delta or 3 Echo, because we've operated from our ham station, which is inside the building at the plant. This year we had to relocate things, so we couldn't use the station, and we went outside. We had a fairly high 20-meter dipole and an 80 through 10 meter end-fed half wave. We only operated this on 80 and 40. It was kind of minimalistic this time. 6 and 2 meter squalo sitting on a pole over here. We had an HF tent and a VHF UHF tent. So this was sort of simple. Built up a little chart for the 2 different stations, for the different antennas. Here were the distances from that station to those antennas. So for the 20 meter dipole and for the end-fed half wave, it was 40 and 80, but 40 is going to be worse than 80 meters in terms of the evaluation. So we just called it 40 meters. And on this chart, we're going to accumulate the power density for each of those for this antenna at that distance, and do that for all those. And then we're going to determine for that particular frequency, what's the maximum permissible exposure, and put that in here. And then we're going to compute the percent of the maximum permissible exposure, and we're going to add those things up. So we'll use the calculator from the fella in the Bahamas, Paul Evans. And in this, we're using 100 watts. All of our antennas were 2.2 dB. From that 20-meter antenna, it was 50 feet away, but he requires that we put the number in meters, and the frequency of operation 14.2, ground effects. So let's take a look. He gives us a lot of information, but the nice thing is because we can put in the exact distance to that 50 feet. I wish he'd let me have the option of choosing feet to enter it, but that's the way it works. The RF power density is 0.0147 milliwatts per square centimeter. He also nicely gives me the maximum permissible exposure, 0.9 milliwatts. So what we're going to do is take this estimated power density and divide it by the maximum permissible exposure. That's this equation right here, multiplied times 100 to get the percent, 1.63. So put that in here, do that for all of the other things that are here. And because we only had one transmitter, we were either operating on 20 meters or on 40 or 80. Then I had to pick the highest value for this. So I just said, okay, it's going to be that one there. 6 and 2 could be there all the time. So that was that percentage. Same thing down here. So for the VHF UHF station, 43% was our maximum. For the HF station, around 22% was the maximum. So that just gives you a quick idea of how you'd handle multi-transmitters. Now, how does it apply to a personal ham station, you ask? Well, at your station, you may have various antennas for high frequency VHF and UHF, so you may have to do various evaluations. You may have an HF station that is on simultaneously with an APRS digipeater that you're operating, or you may have an APRS weather station. Some people are back into packet operation, packet digipeaters, packet bulletin boards, another form of digital station. Some folks are using packet as a way to get into WinLink. WinLink's very popular. A lot of folks doing that. Vera FM, even Vera HF on a separate radio, Pactor HF. You may have other hams of the family. So you're operating on HF. One of your other family members is operating on VHF or UHF. So you want to evaluate both of those stations on simultaneously. So that's the reason we talk about multiple transmitters on at the same time. Well, that's the end of what I'm going to be talking about. Thank you for inviting me to speak on this subject. If you would like to ask me any questions in the future, I'm KR5N at arrl.net, and I'll be happy to answer any questions that you might have.